Salam, peace be upon you. My name is Muhammad Layak Sadiqi, the father of Holophase. Part 15, Book 9.4, Dynamical Grammar. Why some stories happen and others don't. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. You have crossed a significant frontier in Episode 9, the generative grammar. Our climb through the previous books has been magnificent. In Book 9.1, we saw the first production, how the initial sentence of phi generates the entire alphabet of its derivatives. In Book 9.2, we explored topological production, how tears in smoothness create defects with automatic integer labels and braiding statistics. In Book 9.3, we mastered wave and field production, from dispersion and packets to interference and the glorious emergence of coherent fields. We have, in essence, learned how the universe writes. We have studied its grammar, its vocabulary, its capacity to compose sentences and paragraphs. But a profound question has been waiting in the wings, growing more urgent with each new production rule. Why these sentences? Out of the infinite array of grammatically possible phi stories, all the possible ripples, knots, and fields, why does the universe tell the specific stories we observe? A planet orbits in an ellipse, not a square. Light bends at a specific angle in glass. A dropped apple accelerates at 9.8 meters per second squared. The grammar allows countless narratives, yet nature shows a startling preference. Today, we enter Book 9.4, Dynamical Grammar. We move from describing how stories can be written to explaining why some stories happen and others don't. Our anchor image for this entire book is a landscape of hills and valleys, seen from above. Imagine you are planning a walking journey from a village in one valley to a village in another. There are infinite possible paths you could take: up this slope, down that ravine, around the mountain, over the ridge. But if you are a sensible walker, conserving your energy, you will intuitively choose a path that minimizes the total climbing. A path that finds the passes between the mountains, that follows the contours of the land. You are guided by an invisible principle, the principle of least effort. The universe, in telling its phi stories, operates under a similar but exquisitely precise principle. It is called the principle of least action. Today, in our first step into this book, we introduce the core concept: action as a cost function. We will learn how the universe grades every possible history with a single number, the action, denoted S of phi, and then chooses to tell only those stories that make this number stationary, usually a minimum or a maximum. This is not a force. It is a deeper, more beautiful form of narrative economy. Here is the distilled puzzle of this part. We have an infinite set of possible configurations and evolutions for the phi field, all grammatically correct in terms of smoothness and continuity. What rule, written in the language of phi itself, selects the narrow subset that actually occurs in nature? How does the universe choose its history from the library of possibilities? The answer is the concept of action, phi. Think of it as a cosmic scorekeeper, a meticulous accountant. This accountant doesn't look at a single moment. It considers an entire history, a complete possible story of how phi evolves from some starting condition to some ending condition over a span of time. For each possible story, the accountant computes a single number, the action. This number is a kind of cost or effort associated with that particular narrative. But what is this cost made of? In the Holophase language, it is a tally built from phi and its derivatives. Typically, it combines a term that scores how vigorously phi is changing, related to omega squared, a kinetic term, and the term that scores how unevenly phi is arranged in space, related to k squared, a potential or gradient term. For our audio minds, we can think of it loosely as action s equals the time integral of kinetic tally minus potential tally, where the kinetic tally measures the intensity of temporal change, and the potential tally measures the intensity of spatial variation and interaction. The foundational rule of dynamical grammar is then stunningly simple. The actual, physical story that unfolds, the real history of the phi field, is one for which the action S is stationary. This means that if you imagine tweaking the story just a little bit, the action doesn't change to first order. It's at a minimum, a maximum, or a saddle point. In the vast majority of physical cases, it is a minimum. So, among all conceivable paths from start to finish, nature chooses the one of least action, the cheapest story to tell according to its peculiar accounting. This is the principle of least action. From this single, elegant principle, we can derive all the familiar equations of motion: Newton's laws, Maxwell's equations, the Schrödinger equation, Einstein's field equations. We don't start with F equals ma. We start with the definition of the action S for a system. Then, through a mathematical procedure called variation, which is like testing all nearby possible stories, we find the condition for S to be stationary. That condition is the equation of motion. Force laws are consequences, not starting points. Let's explore the triunity of the action principle, the time echo of action, the judgment of entire histories. The action S is not local in time. It does not judge a moment, it judges a complete timeline. This means the universe's choice is holistic. It considers the entire narrative arc from beginning to end. The time echo is this global judgment. A particle doesn't know the force at each instant and blindly obey. Rather, its entire trajectory is selected as the one that makes the total integrated cost of its journey minimal. This gives dynamics a strangely teleological flavor. The final destination seems to influence the path taken, though mathematically it's a consequence of boundary conditions. It is time as a completed story, not just a sequence of moments. The space echo of action, the landscape of configuration. For a field, the action sums over all of space as well as time. It considers the entire spatial configuration at each moment and how that configuration evolves. The potential tally part of the action often depends on the spatial gradients of phi k, penalizing configurations that are too wrinkled or strained. The space echo is this spatial smoothness preference. The field evolves to minimize the total wrinkliness integrated over space and time, leading to the spreading of waves and the smoothing out of irregularities, unless constrained by boundaries or topology. The motion echo of action, the emergence of trajectories. When we apply the least action principle to a particle's path, where the particle's position is derived from the phi field, we get predictable trajectories. For a free particle in empty space, the least action path is a straight line at constant speed, minimizing the kinetic tally. In a gravitational field, the action includes a potential term, and the least action path becomes a parabolic arc or an elliptical orbit. The motion echo is the visible classical path. the actual track through space that we observe, now understood as the cheapest possible track given the universe's cost function. Now, let's locate this monumental concept on the master tree. We are at the very root of the dynamical grammar chunk, a new major trunk growing from the core of Episode 9. This is the node of action S phi as the fundamental selector. It depends on everything that came before. We need to know what phi is, what its derivatives mean, and what constitutes a grammatically correct configuration. It enables everything that follows in this book: the derivation of equations of motion, the connection between symmetries and conservation laws, Noether's theorem, and the introduction of nonlinear interactions. It is the bridge from the what is possible of kinematics to the what actually happens of dynamics. To make this abstract principle tangible, let's light lanterns from across human experience. A near lantern from everyday life. The path you take across a grassy field. You want to get from a gate on one side to a gate directly opposite. The field is uneven. There are muddy patches, slight hills, and a stream. There are infinitely many winding paths you could take. But you, unconsciously applying a principle of least effort, will likely choose a path that is nearly straight, deviating only to avoid the muddiest areas or to cross the stream at its narrowest point. Your brain is minimizing a kind of action that tallies walking effort, muddiness, and steepness. If we could model your brain's cost function, we could predict your likely path. The actual path you take is the one that minimizes your personal action for that journey. A middle lantern from economics and logistics, a delivery truck route. A company must deliver packages to 10 locations in a city. There are billions of possible route sequences. The company's software calculates the action for each possible route, where the cost is a combination of total distance, fuel, time, wages, and traffic penalties. It then selects the route with the minimum cost. The truck's actual trajectory is not determined by a force pushing it to each stop. It's determined by a global optimization of a cost function. The chosen route is the least action path through the day's deliveries. A far lantern from fundamental physics. The path of light. Fermat's principle. Light traveling between 2 points through different media, like air and glass, does not take a straight line if it crosses a boundary. Instead, it bends. Why? In the 17th century, Pierre de Fermat proposed that light takes the path that minimizes the travel time. This is a least action principle where the action is the time taken. Light seems to know the entire path ahead and chooses the fastest one, even if that means taking a longer geometric distance to traverse a slower medium more efficiently. This principle correctly predicts the laws of reflection and refraction. It is a perfect classical example of the universe choosing one story, the light path, from many possibilities based on an extremal, in this case minimal, cost function. From walking paths to delivery routes to rays of light, a universal theme emerges. When a system has a goal, get from A to B, and a way to measure the cost of different ways to achieve it, the actual behavior often converges on the path that minimizes that cost. The universe has a goal, to unfold from initial to final conditions. Its cost function is the action phi. What then is the specific language role of the action phi? It is the master selection rule. It is the grammatical meta rule that operates not on letters or sentences, but on entire manuscripts. It takes the infinite library of grammatically possible phi narratives and selects only those that sit at a stationary point of this abstract cost. It is the rule that answers the question, given all the stories that could be told, which ones are told? The core question this part asks about phi is, what quantitative measure, the action S, can be assigned to any complete history of the phi field, such that the histories which actually occur are precisely those that make this measure stationary? We are moving from asking what configurations exist to what sequences of configurations are dynamically realized. What does the action principle do in the generative process? It selects actual histories from possible histories. It unifies all laws of motion under one common principle, from particles to fields. It provides a powerful computational method. Instead of solving differential equations, you can often find paths by minimizing or extremizing an integral. It reveals deep connections between symmetry and conservation through Noether's theorem, as we will see in the next part. Now, stability and breakdown. The least action principle is a fundamental postulate of classical and quantum physics in their standard formulations. It holds with incredible precision for an enormous range of phenomena, from planetary orbits to particle collisions. It breaks down or requires modification in two key contexts. One, quantum mechanics, where particles do not take a single path but explore all paths, with the action determining the probability amplitude for each path. This is the Feynman path integral formulation, a generalization, not a breakdown. 2. Dissipative systems, where energy is lost to heat, like friction. For these, the simple form of action we've described needs to be extended or replaced by other methods, as friction involves irreversible processes not captured by a simple time-symmetric cost function. Within its domain, conservative systems, the principle is as robust as mathematics itself. This brings us to our disciplined core, falsifiability. The claim that dynamics are governed by an action principle is not a philosophical statement. It is a precise mathematical framework that makes sharp predictions. The central claim. For any isolated physical system that can be described by a holophase field phi, there exists an action functional S phi such that the experimentally observed histories, trajectories, field evolutions, are those that extremize S. Furthermore, if we change the boundary conditions or parameters of the system in a controlled way, the new observed behavior will correspond to the extremals of the same S with the new conditions. A concrete measurement scene, the brachistochrome problem. This is a classic test of least action principles. Imagine a track in a vertical plane connecting a higher point A to a lower point B, not directly beneath it. A bead slides along the track without friction. The question: what shape of track minimizes the bead's travel time from A to B? This is a problem of minimizing an action where the cost is time. The solution is not a straight line, nor a simple circular arc, but a curve called a cycloid. We can set up an experiment with multiple track shapes: straight inclined plane, circular arc, and a cycloid-shaped track, all starting at the same point A and ending at the same point B at the same vertical drop. We release a bead from rest at A on each track and measure the time to reach B with high precision. The pass condition, validation. The bead on the cycloid track reaches point B in the shortest time, and this measured time matches the theoretical minimum calculated from the least action, in this case least time, principle. The trajectories on the other tracks are slower, as predicted. The data confirms that the actual motion, the bead's speed and position over time on the cycloid, also matches the detailed dynamical path predicted by extremizing the action. This experiment, doable in a university physics lab, directly demonstrates that nature selects the path that optimizes a certain integral quantity. The fail condition, falsification. The bead on a differently shaped track, for example, a carefully designed non-cycloid, consistently beats the cycloid's time under identical ideal conditions: no friction, same start and end points. Or, if we use the principle to predict a new optimal shape for a different set of points, A and B, and an experiment with that new shape shows a travel time longer than that on a shape guessed by some other rule, the least action principle for this mechanical system would be falsified. It would mean that for sliding beads, the cheapest story according to our proposed action is not the one nature tells. This would force a radical reconsideration of the foundations of mechanics. This falsifiability ensures that the profound elegance of the action principle remains accountable to simple, tangible experiments. Let's cultivate a practical recognition skill. You can train your mind to see least action logic in any system where behavior appears optimized with respect to a clear, quantifiable cost, and where the system seems to explore alternatives to find an efficient solution. Watch a river finding its course down a mountain. It doesn't take a random, jagged path. It erodes its channel along the path of least gravitational potential energy over its length, which often leads to meandering curves that balance direct descent with erosion resistance. Its course is the least action path for water flow given the constraints of the landscape. Observe a soap film stretched across a twisted wire frame. The film forms a minimal surface, the surface with the smallest possible area given the boundary. Area is its action. The film physically probes possibilities and settles into the configuration that minimizes this action, creating beautiful, saddle-shaped surfaces. Consider an investor balancing a portfolio. Given a desired return, they often seek the portfolio with minimum risk, or given a risk tolerance, they seek maximum return. This is an optimization problem. The chosen portfolio is the extremal one, according to their financial action function. Their buying-selling trajectory through the market aims to reach this optimal state. When you see a system that consistently settles into a state or follows a path that appears efficient, optimal, or smoothest according to a measurable quantity, you are likely seeing a manifestation of an extremization principle. You are seeing dynamics as an optimization story. We must connect this foundation deeply to our Holophase journey. In all previous books, we build the stage and the actors. Now, with the action principle, we have found the director. The director doesn't micromanage every motion with forces. Instead, the director gives the actors a single, simple instruction. Perform the story that has the lowest overall production cost. The actors, the phi field and all its derivative patterns, then work out the details themselves, resulting in the majestic, coherent dynamics we observe. We haven't added a new entity called force. We've discovered a higher-level grammatical constraint that generates what we call force laws. If you want to see the full mathematical derivations and exact equations behind this idea, the calculus of variations, the Euler-Lagrange equations, the construction of Lagrangian density for fields, you can search for Holophase on Zenodo. There, you will find the scientific papers that this audio journey is built on. Let us pause and feel the magnitude of this step. With the introduction of the action S-phi, we have reached the conceptual core of theoretical physics. We now have a complete two-part generative engine for the universe. The Kinetic Grammar, books 9.1 to 9.3, that defines what configurations and patterns are possible: letters, words, sentences, paragraphs. The Dynamical Grammar, beginning here, that defines which of those possible stories are actual by selecting those with extremal action. The universe writes itself by first allowing all grammatically correct tales and then telling only the cheapest ones. In the next part, we will build directly on this foundation. We will discover a staggering consequence of the action principle, Noether's theorem. This theorem states that for every continuous symmetry of the action S, there is a corresponding conserved quantity, a permanent number that does not change throughout the story. If the action doesn't change when we shift in time, we get conservation of energy. If it doesn't change when we shift in space, we get conservation of momentum. If it doesn't change when we rotate, we get conservation of angular momentum. The deepest laws of conservation, the time, space, and motion echoes of permanence, will emerge directly from the symmetries of the narrative cost function. Before we end, the mandatory zoom out to hold our scope. The actions phi, for all its power, is still a functional built from phi and its derivatives. It is a specific way of tallying and integrating the intensities of change, omega and k, that we identified at the very beginning. We have added no new substances. We have simply identified the master grammatical rule that selects narratives from the set of possibilities generated by the single continuous field. One field, phi, plus its infinite tower of derivative questions, plus the principle of least action. With this, we can, in principle, generate all of classical physics. The journey from alphabet to epic has found its plot selection mechanism. As we conclude, hold the image of the landscape of hills and valleys. Each possible path of the walker is a possible history of phi. The height of the terrain at each point represents the local cost rate. The total action is the integrated height along the path. The walker, the actual universe, does not blindly stagger. It finds the mountain pass, the gentlest valley, the route that requires the least total climbing. It moves along the path of least action. The landscape is sculpted by the nature of phi itself, and the journey taken is the one we call reality. The universe is not pushed. It is finding the most economical way to be. Salam, and peace be upon you.